We are excited to present SEBRA, a research project developing a safety awareness system for bicycles with a scope to increase safety. I'm Henrik. I'm working at the Active Advanced Engineering organization, and I've been working with road safety in the automotive since my days in university. The world of mobility changes, and our mission at Active is to help create a safer, greener and more connected world. This is what moves us to develop solutions to the challenges these trends create. With the rising environmental awareness, more and more people use bicycles in their daily commute, and the increased bike traffic, along with the already chaotic vehicle and public transport in bigger cities, cyclists become even more vulnerable to accidents. With Active's award-winning 76 GHz radar technology, we are addressing one of the challenges, safety for bicyclists. The SEBRA project is a partnership program funded by the Swedish government and in collaboration with RISE, Research Institute of Sweden, and LIRI, a small e-bike company in Gothenburg. Active is part of the road transport research community in Sweden, SAFER, where RISE also is active. We have had several discussions on how to make roads safer for two-wheelers, and in recent times also how automated vehicles shall interact with other road users in a safe way. The black box in between the frame of the bike is the instrumentation, and only the radars will be part of a product solution. The project group will tell you more about the project, but in general, Active's radar technology is small, power efficient, and to a price point where a market introduction is valid for this application. The project consists of, from RISE, Jonas, our project manager, control over all admin. We have Tan, Astra, David and Victor, our HMI researchers. And for Active, we have Tobias, our technical lead, always with a solution. Josef, our feature function expert, and our students, Hugo, the mechanical expert with a sense of humor, Philip, our software and mechanical expert in one, and Olle, an engineer with a feeling for design. And from Liri, we have Linus, our e-bike expert.
My name is Jonas Andersson. I'm a senior researcher at RISE Mobility and Systems. The SEBRA project is all about exploring active safety systems for future e-bikes to see how this technology can improve the safety and comfort in the future. The system detects other vehicles in 360 degrees, and to others it signals using light by blinking if a vehicle comes up too close, too fast, for example. And to the bicyclist, it also signals using vibrations in the seat and in the handle, and also has a small screen for other information. We have evaluated the system with over 40 bicyclists and drivers, and we believe that it can improve road users' awareness of each other. We think that it can improve comfort and safety and reduce the number of incidents and accidents if we develop it further. To us, this is a research platform that we can use to study how bicyclists interact with other road users as well. We can also use this knowledge to provide guidance for future safety improvements on bikes, vehicles and infrastructure. The system is still a prototype, and our next step is to make it even better so that we can continue to explore new active safety systems for e-bikes even further.
The project aims to extend the current knowledge about problems, solutions and possibilities within the specific area of active safety. The main research questions included how and when to warn a bicyclist against oncoming danger from rear, side and front, and how to communicate and make the oncoming vehicle aware of the bicyclist.
The first prototype was built with everything externally and easily accessible. We used sensor stabilizers where we could compensate the roll angle and thereby achieving horizontal input from surroundings even when actually turning the bike. As a light source, a pulsating hazard warning light from a forklift truck was used to clearly see triggers. A small PC or a NUC was used as the main data log recorder, and we also used a webcam in the front and in the rear to be able to navigate more easily when analyzing logs. When we built the second prototype, we had the goal to hide the entire log system inside the frame of the bike, making it more user-friendly, but also giving it a more futuristic look. The prototype has the Wi-Fi router connection needed for a 360-degree view of the bicyclist's surroundings on the actual telephone app. It has rear and forward LED warning lights, which are triggered depending on the actual traffic scenario. The bike hosts an IMU, inertial measurement unit, consisting of a 3-axis gyroscope and a 3-axis accelerometer. The purpose of the IMU is to measure the yaw rate and the roll rate of the bicycle. A quadrature encoder is mounted to the front brake disc of the bike. Encoder provides measurements of the bike's speed.
To make other road users aware of the bike and warn them in case of potentially dangerous situations, LED lights are mounted in the front and rear of the bike. The LEDs are controlled by a microcontroller, Arduino Nano, which is connected to the PC via USB.
We installed haptic motors in both the left and the right handlebar, but also in the seat of the bike. Like the LEDs, the haptic motors are controlled by a microcontroller, the Arduino Nano, which is then connected to the PC via USB. Unlike cars, bicyclists are more vulnerable to motorists approaching from behind, so we needed a system with long-range detection radars in the rear and a wider range detection area in the front of the bike.
The radars alone can detect stationary objects but cannot differentiate between objects and scenery. In car systems, the information is fused with camera information to solve this issue. However, collision with stationary objects is not tackled within this research.
Well, the output of the 4 radars go to the tracker module. The tracker runs on the Intel NUC PC and is responsible for processing the radar detections. The tracker then uses measurements of the speed and the yaw rate to be able to distinguish between stationary and moving objects. You can then connect your own Android phone to the actual bike, getting a Wi-Fi connection provided by a small router that we hid inside the frame. By connecting this smartphone to the bike, it's actually possible to live stream what the sensors are picking up and detecting. The arrow points out the host or the SEBRA bicycle, as you can see here, and all the moving objects in the radar's field of view will show up on the screen in the form of red rectangles.
The feature function software is responsible for analysing the output from the tracker data and to assess whether the current situation is dangerous. The feature functions consist of a front and rear warning. This software is also used in automotive applications, however it has been adjusted for the bike's specific use case. The human-machine interface, HMI, is responsible for providing the bicyclist and surrounding vehicles with information from the tracker and the feature functions. The HMI towards other vehicles consists of the front and rear lights. The lights flash when a vehicle approaches the bike. The HMI towards the bicyclist consists of vibration motors in the seat and in the handlebars. When a warning is triggered, the seat and the handlebars vibrate according to which side the vehicle is approaching from. There is also a visual HMI for the bicyclist in the form of an Android application. The bike itself and the adapted warning functions were intended as proof of concept and not as a ready-to-market product.
The SEBRA project has investigated how a radar system can enable the advanced safety functions accessible for bicyclists. Reconfiguration of radar settings and related safety software has been performed based on the accident pattern analysis.
The project paves the way to include vulnerable road users as active participants in the future of smarter, safer, and more reliable mobility ecosystems.